Jai Hind to all. This is Dr. Shivani Agarwal. Today I am going to present the topic paging. So, in this topic we have to cover why paging occurs, what is paging, how we have to implement the paging concept, what type of algorithms of the paging we have. So, let's start the basics about paging. So, paging is what? Paging comes from the concept of the non-contiguous memory allocation scheme. The paging and the segmentation both are the policies of the non-contiguous memory allocation scheme. Paging is a storage mechanism that allows operating system to retrieve the processes from the secondary storage to the main memory in the form of pages. This is a very important concept, that we have to retrieve the process, not the complete process, but the smaller pages come from the secondary storage to the main memory. That topic name as paging. Basically, it involves the breaking the logical address. Logical address means CPU always generate the logical address. That address belongs to the secondary memory, and these addresses have a fixed size of blocks. That block name as page. Page size equals to the frame size. This is a very important point, that you have to always keep in your mind, that page size equals to the frame size. Page size belongs the process. That process resides in the secondary memory, and the frames belongs from the main memory. So, CPU generate the logical address. We have to translate that logical address to the physical address for retrieving any information from the main memory. So, this is the basic concept about the paging. So, this is the block diagram of the main memory and the secondary memory. Main memory divide the process into the frames, and secondary memory divide into the words, and each word named as a page. So, we want to swap the process from the secondary to the main. So, one page transformation to the frame. So, block of the secondary memory size same as the main memory size, that I already explained. Because of the equal size, we have to transfer the data from the secondary to the main memory. So, the size of the page and the frame are not differed. This is a very important concept, that the page size equals to the frame size. That already given, that frame size equals to the page size. In this particular problem, if a process x1 has pages, 3 pages, p1, p2, p3. Suppose we have a process, this is a process named as x1. This process has 3 pages. Suppose we have 3 pages, p1, p2, p3. These 3 pages exist in which memory? In the secondary memory. These 3 pages p1, p2, p3 exist in the secondary memory. So, I suppose that these pages are in contiguous fashion in the secondary memory. Contiguous means one by one, p1, p2, p3. That is not in the scattered fashion, that is p3 is upper than the p2, p2 is upper than the p1. So, this is in scattered, not in the scattered fashion, this is in the contiguous fashion in the secondary memory. So, find out how many frames required in main memory for storing the process x1 where they will save. This is the question. So, actually the question solved by using this particular diagram. This is a diagram of secondary memory, and in this diagram we have 3 processes p1, p2, p3, all the 3 processes in the contiguous fashion, but when we transfer these processes from secondary to main memory, so it transfer, these 3 processes transferred into the non-contiguous fashion, because this is not in the contiguous form. P3 is the highest mode, then P2, then P1. First we have to find the space for P1. So, we look the space in the bottom of the memory. So, it is P1, and then the free space P2 is required. So, this data is executed. So, this P2 space is this particular space, but that is not in the contiguous fashion. This diagram shows that 3 processes are saved in the secondary memory, but not in the contiguous fashion. So, it is not compulsion that the space needs in the contiguous fashion. So it proved that paging avoids the external fragmentation because we don't need the contiguous fashion memory allocation in the main memory. So that avoid the external fragmentation. Now, in non-contiguous fashion scheme, how we translate the logical address into the physical address? Because we know that the CPU generate the address, that is the logical address, and there is no ordering of page, that how we find the address. So that address we have to convert from logical to physical, because this address tell about the location of the secondary memory, but we don't know about what the process cover the address of the main memory. So this address we have to fetch the translation of the logical address into the physical address. So basically the logical address divide into the two parts, or address divided into the two parts. First is the page number, second is the displacement. Displacement is what, or page number is what? Page number means which page you have to want to change, and displacement means which location of that particular page. Suppose a page consists of 4 words, 0, 1, 2, 3. Suppose this is a page. This is a page P1. Each page consists of 4 words. This is A0, this is A1, this is A2, this is A3. So we have to recognize the page with the number is 0, 1, because P1, the binary of 1 is 0, 1. So P1 recognized in the binary form is 0, 1, and each word is also represented in binary is 0, 0, 0, 1, 1, 0, 1, 1. So when the address is 0, 1, 0, 1, that means the page number is 0, 1, means P1 page, and the displacement is A1, because the number address is 0, 1, 0, 1. So this is the page number and the page displacement. So address generated by the CPU is divided into two parts, page number and page offset. Offset is also same as the page displacement, both are the same things. So what is page number? That define how many bits in page number. So we calculate the total number of page. Suppose we have the address page, suppose 6 bits. So how many pages are there? 2 to the power 6, that is 64 pages are there. So P0 to 63, these are the number of the pages, and each page has the 4 words. So each word represent the bit is 0, 0, 0, 1, 1, 0, 1, 1, but including the displacement we have to put the page number also in this particular given page. So this is created the logical address. Now the page table. In the non-contiguous memory allocation scheme, we use the linked list, but this is not suitable in paging because it is a very slow process. So solution of this particular problem can be solved by using the page map table. So in this page map table, we have the page numbers with the frame numbers. So we know about that the page number belonging from the secondary memory and the frame number belonging to the main memory. So which page number we have to assign as which frame number. So this is a very unique process of page map table. Now this is the concept of the translation of the logical address to the physical address. So we know that CPU generate the address name as the logical address, and this address divide in the page number and the page displacement. This is known as the page number. This D denotes the displacement. Displacement or page offset. Both are same. In the previous slide I already explained. So CPU generate the address name is the logical address. This address translate to the physical address because we deal with the main memory and we fetch that which frame we have to put which page number, which page. So this translation we have to do by using the page map table. In this page map table we have find which page number belongs to the which frame number, and the displacement is also always same in these translation schemes. When the logical address have the 4 words in a page, so frame have also the 4 words in a frame. So this is the same. So we have to find, suppose we have to find that P1 have the process F1. So this P1 page we have to find the F1 and which particular data you have to need for verifying the page to the frame. So it is, we have to identify with the displacement. Suppose this is 0, 1, so this is also the 0, 1. So exactly we have to fetch the data from the main memory by using the address translation scheme from the logical address to the physical address. This is the diagram of the main memory. This is the physical memory basically. So we fetch the data or the information about that particular data from the main memory by using the paging scheme with the address translation from logical to physical. So the disadvantage of that is, due to the fixed size partition, it has internal fragmentation, but it is avoid the problem of the external fragmentation. This is the advantage of that. And each process has individual PMT, and each and every PMT we have to store in the main memory. So the process frequency becomes slow, because of that the access time is double. First we have to search the PMT and find out the PMT in the main memory. Then we have to find out which frame number that particular page is stored, so that we have to find the physical address for that. So this is the slow process due to the double access time. So these are the disadvantages of that. Now we take the numerical. We have address size equals to 10 bits. So find out how many frames in memory and what is the size of memory. So basically memory size is n multiplied by bytes. So there are the address bit is 10 bits. So how many pages are there or how many frames are there? This is 2 over 10. This is the address bits of the main memory. So when it is 10, that means it is basically 2 to the power 10 for finding the total number of frames. So it is what? 1024. 1024 the total frames are there. So the size of memory is n multiplied by the bytes. Byte means 1 byte. 1 byte equal to 8 bits, because the formation given in the bit form. So it is basically 1024 multiplied by byte. So it is 1 KB. This is the solution of the first question. Now the second is what? In the second question we required how many bits are required for the address. Now in this particular question we have the complete size of the memory. It is 64 KB. So first we have to convert this 64 KB equals to 2 to the 6 dot 2 to the 10. 10 for what? 1K equal to 1024. So it is 2 to the 10. So it is basically 2 to the 16. So the address bit in this particular case are 16. 16 bits are required for the address. Now how many bits are required for the address? So 16 bits are required for the address. Now find out the locations of the memory. So it is 0 to 65535. Total locations are 65536 due to the 2 to the 6, 16. So it is basically 65536. So the starting address with 0 and the end address with 65535. So it is the second numerical. Now take the third numerical. In the third numerical we have a logical address, that is 24 bit, and the physical address. So logical address belongs to the secondary memory and the physical address belongs to the main memory. And we have a page size. Page size is 1 KB. So we know that page size always equals to the frame size. If the page size is 1 KB, so frame size is also 1 KB. 1 KB means we have the total address bits are 10 over there, because it is 1024. So it is recognized by the 10 bits. Logical address is 24 bits. So basically we know that logical address is the page number and the displacement. Complete bits are 24 bits. And we know that the displacement bits are 10. So it is 10. So the page bits are 14 in this particular case. So this is what, how many pages in the secondary memory. So how many pages are there? These are 2 to the power 24 total pages, and with respect to the pages, 2 to the power 14 is the page, and total size is 2 to the power 24. So logical address size is 2 to the power 24, and this address divided into the two parts, page number and the displacement. So in this particular example, total number of pages are 2 to the power 14 and the displacement bits are 10, because we find out how many bits in the page number, how many pages in the secondary memory and the main memory. So in the secondary memory we have 14 pages and the total pages in the secondary memory are 24. Okay, but by the division of that, 14 pages are required in the secondary memory and 10 bits are used for the displacement. And in the main memory, the size of the physical memory is 16 bits. 10 bits are used for the displacement, to 6 bits are used for the physical memory or the main memory. So these are the number of frames are present in the main memory. Now we move to the next topic, that is a page replacement algorithms. Page replacement means what? We need to decide which page needs to replaced from the which page if the main memory is full. If the main memory is full, so we have to just swap in or swap out concept is used, that concept known as a demand paging, and we require that page first the CPU fetch the data from the page map table. If that particular page is not present in the main memory, so we have to just swap out that particular page from the secondary memory and swap in the main memory. And because the main memory is full, so we just swap out from the page of the main memory, one page from the main memory, and send back to the secondary memory. So this is the basic requirement of the page replacement algorithm, because we need that particular page that we demand for the use. So this is the basic 3 algorithms of the page replacement algorithms. So first is FIFO, second is LRU, and third is optimal. FIFO means first in first out. So we just replace the oldest page that comes from the main memory from the longest time, and it is implemented by keeping track of all the pages in the queue. So take the numerical for that. In this particular numerical we have the 3 page frames for storing the page in the main memory, and initially we think that the page frames are empty, the stack is empty, and we put these particular page for the processing. So calculate the hit ratio and the miss ratio. So in this example we start with this particular frame. In this particular frame we have the 3 frames. So initially the stack is empty, so we just fill with the number is 4. So first we have to put the number 4, then 7, then 6. So we have to just initial frame, we have 3 frames, and these frames are filled with the 4, 7, 6. Now when we want to fetch the data from as 1 in this particular frame, so which frame we have to swap out, and this particular number we have to put in this particular main memory. So which number we have to swap out from this particular frames. So in these blocks we have to swap out the oldest page, and the oldest page number is 4. So we have to swap out this and swap in the 1 in place of 4. Now 7, so 7 is always present in this, so it is hit. Now again, so it is hit. Okay, 7 is hit. Now is 6 is also present in the frames, so it is also hit. So there are 2 hits over there. Now 1 is also present in this, but always keep in mind when the 7 is comes previous in this particular frame, and again it is recalled, but it is counted as the oldest one. So this is the basic difference with the FIFO and the LRU also. And now 2 in the place of 7, because 7 comes after 4, so it just swapped from the value, that is 2, and now 7 is placed in the place of 6, because 6 is the oldest one, and now 2. So in this particular problem 2 is always also present in this particular frame, so it is also hit. So there are 4 hits with respect to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 we have 10 elements, but there are 4 hit only. So the hit and miss ratio is this: 10 minus 6. 4 is the hit ratio and the miss ratio is 60% over there. This is the miss ratio, it is 60% in this particular example. Now LRU. LRU means least recently used. So the basic difference of LRU and FIFO is that In the FIFO, we always counted the oldest is the oldest one, but in the least recently used, if the recalling is present, so that particular element we have to count as a new one. So this is the basic difference between the LRU and the FIFO. So the same example for the LRU is that first the frames are empty, so we have to put the 4 in this, then now the 7, now 6. So these frames are same as the FIFO, but when we put the new element, that is 1, in place of, for what? In place of 4, because 4 is the oldest one. Now this is the new element, and in current phase this is the new element. So these two elements are not swapped. Now 7 is come, 7, when the 7 come, so it is hit because it is already present, so it count as a new one, not the old one. So we don't swap when we want to swap out or swap in, so we don't swap 7 at that present time. Now the newest element are 1 and 7. So 6 is always hit, so 6 is present as a new one. So 6 and 7, they are the new elements, counted as a new element. 1 is also present, so it is also hit. Now the 1 is the highest new element. So we don't swap 1 and 6 over there. Now we put 2. So in which place we have to put the 2 number? So we have to swap the 7 number in this place. So now 2 is counted as new. Now 7. So we don't swap 1 and 2 over there. So we swapped 6. So this is the 7. This is counted as new. Now 2. So 2 is also present in this particular field frames. So it is 1, 2, 3, 4. In this particular example, the hit ratio for LRU and the FIFO is same. There are 40% and the miss ratio is 60%. Now take the same example for the optimal. So optimal means just see about the future. If the future, that particular element for the longest time, so we don't change that particular element that we required in the future. So this algorithm is used for the future prediction, and it is the best algorithm and give the least number of page faults. So take the example for same example for the optimal. So we just put 476 in the same process like as FIFO and LRU. Now we put 1 in which place? So first we have to see the reference numbers. So in the reference numbers, 7 we counted just say after 1, so it is not swapped, and 6 it is also not swapped. So we have to swap the 4. There is no need in the future, so we have to replace 4 in this particular scenario. So we have to swap the 1 from the 4. Now 7 it is hit, 6 it is hit. Now 1 is also hit. Now 2. Which frame we have to replace 2? So just see the future, and at that time we have 176. So 7 we record, so we don't swap the 7 over there, and 1 and 6 we have to replace 1 and 6. So when we have the 2 element, then we apply the FIFO on that. So in this scenario, we just we have swapped 1 in the oldest, but the oldest one is 6. So we just change the 6 from 2. So it is put in the place of 6. So this is the optimal algorithm for the page replacement. So in this particular example, we have 1, 2, 3, 4, 5. 50% are used for the hit ratio and 50 is used for the miss ratio. So thank you.